In this experiment, we're going to be testing Markovnikov's rule by performing an anti-Markovnikov addition of water to an alkene 1-hexene, and we expect to be forming the anti-Markovnikov product 1-hexanol. We are going to be testing our product to verify that we do not form any of the Markovnikov product 2-hexanol, so none of this product is expected to be formed. This is a multi-step reaction. In step 1, we're going to be using sodium borohydride and iodine in a THF solution. Tetrahydrofuran is just an ether and a really good solvent. And then in step 2, we'll be adding our hydrogen peroxide, which is what makes this anti-Markovnikov, and also a little sodium hydroxide. This reaction uses a technique called addition under reflux. Even though we technically aren't going to be doing a reflux at all in this reaction, we will be using the same set of glassware. Our reaction is one that generates a lot of heat. So instead of putting our round bottom flask in a sand bath to heat it up, which what we would be expecting for reflux, we're going to be having an ice water bath down here to keep the reaction nice and cold. And in our round bottom flask, we'll be putting our 1-hexene, our reagent. We'll also be putting sodium borohydride, NaBH4, and we'll be putting a little bit of the THF solvent in there as well. This piece of glassware right here, which we haven't used before, is called a Claisen head or a Claisen adapter. And as you can see, it serves the purpose of just splitting the opening of the round bottom flask into 2 openings. So this allows us to connect 2 things to the round bottom flask. One of the things that we'll be connecting is a separatory funnel, which we're familiar with. The other is a water condenser, which you're also familiar with. As a reminder, water goes into the bottom port of the condenser and it comes out the top port of the condenser. And again, as I said, we're not actually doing a reflux in this reaction. This reaction here generates a lot of heat. So the reflux is here to help cool down anything that might come out as this reaction generates heat, just in case our ice water bath fails. Inside the separatory funnel, this is where we will be putting the iodine mixture in, it's dissolved in THF, and we'll be adding this to the reaction flask through the separatory funnel. Using the separatory funnel allows us to have a real slow and controlled addition of the iodine to help control the reaction because it is so exothermic and generates a lot of gases. One last thing that I want to point out, when you're doing addition under reflux, it is really important that you assemble the glassware in this particular direction so that the separatory funnel is directly above the round bottom flask, and as the solution is added, it's going to be able to go straight down the round bottom flask. What you don't want is to reverse the position of the sep funnel and the condenser. You don't want to be draining your solution down the curved portion of the Claisen adapter, and that's just not very efficient. Let's assemble our glassware for addition under reflux. For this, we need a round bottom flask, and we'll be putting it in this dish, which will be containing an ice water bath. We also need a water condenser, and we need a separatory funnel. And last but not least, we need the Claisen head or the Claisen adapter. We will be attaching the separatory funnel to the straight portion of the Claisen head, and the water condenser will be attached to the curved portion of the Claisen head. We'll be attaching the Claisen head from this curved portion right here to this 3-prong clamp that we have on our ring stand. I'm going to begin by greasing the Claisen head, the bottom portion of the Claisen head that will go into the round bottom flask. And then once I get that joint with some grease on it, I'm going to attach from the curved portion, I'm going to attach the curved portion to this 3-prong clamp. The straight portion is the part that I will be attaching the separatory funnel to so that it can drain directly down into the round bottom flask. The next piece that I'm going to attach is the separatory funnel. It's going to go right into this ring that's going to help suspend it. I'm greasing the joint of the separatory funnel as well because that's going to be fitted into the Claisen head. And I'm going to slide this into the ring that will help support it. Remember, I want to twist the glassware together to help spread the grease around. And once I get it nice and secured in place, I'm going to be using this blue clip. It's called a Keck clip that helps to hold those joints together to make sure that they're nice and secure. Then I'm going to go ahead and add my water condenser. I also want to make sure that this joint has a good amount of grease on it. We want to make sure that all of our joints are sealed up nice and well. I'll be placing that behind the separatory funnel, so it'll be a little bit hard for you to see. I'm twisting it to make sure that I get a good spread of grease, and then using another Keck clip to secure that water condenser to the Clason head. Once everything is in place, I'm ready to position my round bottom flask. I've got a little stir bar in there already ready to go, and it is going to be positioned underneath this whole entire thing. So I'm going to loosen this clip that allows me to raise all of the glassware up and drop it all back down. Because everything is secured with these Keck clips, I can move all three of these pieces of glassware all together at the same time. Now that the glassware is assembled, we're ready for our reagents. I have already put the 1-hexene reagent into the round bottom flask. We're going to be using about 20 millimoles of 1-hexene. The next thing that we're going to be adding is our solvent. The solvent in this reaction is tetrahydrofuran, or THF. This reaction calls for 25 milliliters of the THF solvent. I haven't pre-measured the THF solvent because it is extremely volatile, which means that it evaporates really, really fast. So off screen here, what I'm doing right now is just pouring out the 25 milliliters of THF that we need. I know you can't see that, but it's not very exciting. And now that it's measured out, I'm just going to add it into the round bottom flask. Because THF is our solvent, it's okay if we have a little bit extra in there. It's okay if it's not exactly 25 milliliters. Our last reagent for the round bottom flask is the sodium borohydride. It is this white powder. I have already pre-weighed about 8 millimoles of sodium borohydride. It's a really fine white powder, kind of difficult to work with. So I'm gonna curl up this side of the weighing paper, and I'm gonna try to create a little funnel with the weighing paper to make it a little bit easier for me to transfer it into the round bottom flask without making too much of a mess. I don't know how easy it is for you to see this or not, but I've got a couple of grains of the sodium borohydride up at the very top of the round bottom flask where the joint is, the location where the Clason head needs to attach to the round bottom flask. And that's definitely not what I want. We always want to avoid having any chemicals along the joints of our glassware. It can cause the glassware to fuse together, which would mean that we can't pull the glassware apart. So what I need to do is rinse those granules of sodium borohydride down off that joint and into the flask. And I'm going to do that using a little bit of my solvent THF. Remember, it's okay if I have extra solvent present. It's not a reactant. It's not going to affect the reaction at all. Now I've got my joint cleaned up. I am going to nestle this round bottom flask into the ice bath. And once I get it into a position that I like, I'm going to loosen the clamp on my glassware, lift it up, and then drop it back down into place. Those Keck clips allow me to move all of this glassware all together without worrying about it loosening or falling apart. So now everything looks nice and secure. All of the reagents that I need are in the round bottom flask, and I've got the solution stirring, ready to go. It looks good. The last thing that we're going to be doing is adding our iodine THF mixture to the separatory funnel. I have pre-weighed 4 millimoles of iodine and 8 milliliters of THF into this small vial and mixed it up together as a solution. And I'm just going to be transferring this solution into the separatory funnel. Stop clock is closed. I want to make sure that I add the iodine solution to the round bottom flask very slowly. So I don't want this to be added too quickly. The iodine solution is pretty difficult to transfer. I'm going to use a little bit of THF to rinse out the little vial. There are some chunks of iodine that didn't completely dissolve in that little vial that I know you can't see, but I want to make sure that I get total transfer of all of the iodine. And also you might notice that there's some iodine up at the top of the joint of the separatory funnel, and I'm going to try to rinse that down as best I can. So here I'm just rinsing out that little vial, trying to get all the pieces of iodine out of the vial. And now I'm trying to clean the separatory funnel up as best I can. Iodine is really, really messy to work with. No matter how careful you are, it always ends up getting all over the place. So now it looks like we have all of our reagents ready, and we are ready for this reaction to begin. We're almost ready to add the iodine THF solution from the separatory funnel to the round bottom flask. All that's left is connecting our condenser to water. Remember that water goes into the bottom port and it comes out the top port. And once we get all the tubing connected, then we can slowly turn the water on. I'm just holding that tubing in place as the water gets started to make sure that it doesn't slip off the condenser. And I'm turning the water on really slowly also to minimize the possibility that the tubing will pop off of the condenser. Now that our water is flowing, we're ready to begin adding the iodine THF solution. So the instructions tell us that we want to add this about 20 drops at a time, which is about 1 milliliter. And that's pretty difficult to gauge with a separatory funnel. As you will see here, it doesn't really drop out. It just kind of drains out. So I'm just going to take my best guess. It's definitely going to be okay if I don't add a whole milliliter or a whole 20 drops at a time. If I add a smaller volume, that's fine. So I'm just going to err on the side of caution and add a small volume. And as you can see that this caused the solution to turn kind of an amber brown color, we want to allow it to stir and react until the solution in the round bottom flask changes to a pale yellow color. We're not exactly sure how long that's going to take. We just have to wait patiently. The instructions do say that if the color has not changed within 5 minutes, we can go ahead and add a second portion of the THF iodine mixture. So I'm just going to be monitoring this, looking for the pale yellow color change, and also simultaneously watching the clock. Every time the color changes to yellow or 5 minutes has passed, I'm going to add another small portion of the iodine THF mixture. And I'll repeat this process until all of the iodine has been added. All of the iodine THF mixture has been added from the separatory funnel into the round bottom flask. And this reaction just needs to sit and stir overnight just to make sure that we completely finish step 1 of the reaction. So I'm going to disassemble this glassware for the overnight stirring period. This will give me an opportunity to clean the glassware for the second step of the reaction, which we'll do tomorrow. Also, in general, it's a good idea to always disconnect your glassware whenever possible, to not leave it connected overnight, just to minimize the possibility of the joints freezing together. Because THF is such a volatile solvent, meaning that it evaporates really easily, I definitely don't want to leave this round bottom flask open overnight, stirring. If I did that, I would definitely expect to have quite a bit of my THF solvent evaporating. So I'm going to want to cover the opening of this round bottom flask for the overnight stirring period. There are corks and stoppers and things that you can use to plug the opening of a round bottom flask to minimize evaporation, but I've had some bad experiences with those being sucked down inside the round bottom flasks. So I prefer to use something like this film to cover the opening. I don't have to worry about this getting sucked into the round bottom flask. This is a lot like saran wrap that you would use in your kitchen. It's just a bit thicker. And so once I get a nice piece cut, I'm just gonna stretch this over the opening of the round bottom flask. It doesn't really stick onto the glassware the way saran wrap might, but the arms of the 3-prong clamp are gonna help hold it in place to make sure that I get a pretty good seal and I don't have to worry too much about the evaporation. I'm leaving this on the hot plate just for the stirring aspect of the hot plate. There isn't any heat being added to this round bottom flask, and it's just gonna sit and stir overnight and finish reacting. This reaction has been stirring overnight, and we are now ready for step 2 of the Anti-Markovnikov addition of water to 1-hexene. Before we add the hydrogen peroxide and sodium hydroxide necessary for step 2 of this reaction, we're going to begin by just simply adding some water to decompose any excess sodium borohydride that might be left over from step 1. We have no way of knowing if there's any excess sodium borohydride present in the flask, so we're just going to add water and see what happens. If there is sodium borohydride in the flask, excess left over, we're going to see quite a bit of fizzing, things like that going on. This is a pretty exothermic reaction, so as we add the water to decompose excess sodium borohydride, we're going to want to keep our flask in an ice bath just to help control the heat. Once all of the fizzing stops, then we can go ahead and add the reagents for step 2 of this reaction. We're going to be adding the sodium hydroxide first, and then we'll follow that up with the hydrogen peroxide. I am reassembling our glassware for addition under reflux. I'm going to be using an ice bath to keep the round bottom flask nice and cool. And we're going to be reattaching the separatory funnel as well as the water condenser and getting the water flowing through the water condenser before we begin adding the reagents that are necessary for step 2 of this reaction. Now I'm going to add 10 milliliters of water through the separatory funnel to decompose any excess unreacted sodium borohydride that's left over from step 1. If there is any unreacted sodium borohydride in the round bottom flask, we're going to see some fizzing. The amount of fizzing that we see really depends on how much sodium borohydride is in the flask. After all of the water has been added to the round bottom flask, I'm going to let it sit and stir just for a few minutes to make sure that the water has a chance to react with and decompose all of the excess sodium borohydride that might be present in the flask. And once that's done, I'm going to move on to adding the reagents for step 2 of the reaction. For step 2, we'll keep our round bottom flask in a water bath held between 30 and 40 degrees Celsius. The first reagent that we're going to add is sodium hydroxide. The instructions called for 2.3 milliliters of 3 molar sodium hydroxide, but all I had handy was 6 molar sodium hydroxide. So what I've done is cut the volume of sodium hydroxide in half and mixed it with water. This is going to give me a total of 2.3 milliliters of 3 molar sodium hydroxide. I'm adding this straight to the round bottom flask through the separatory funnel. Notice that the stopcock on the separatory funnel is open. This is not a reagent that I need to add slowly or carefully to the round bottom flask, so I'm just pouring it straight in. And I'm going to give that about a minute to mix in the round bottom flask before I add the next reagent. The next thing we're adding is 30% hydrogen peroxide. The instructions call for 4 milliliters, which I've already measured. This is something that we do want to add slowly and carefully, so I'm closing the stopcock on the separatory funnel. This is the really exothermic part of the reactions. This is where we're going to need to be really careful about monitoring the temperature of the water bath, not letting it get up above 40 degrees. I'm going to adjust the stopcock on the separatory funnel so that it just allows the hydrogen peroxide to drip slowly And if I notice the temperature starting to go up too much or like the reaction looking a little bit too violent, then I can close the stopcock on the subfunnel and stop the hydrogen peroxide temporarily. As the hydrogen peroxide is being added, you're going to notice quite a bit of reaction down in the round bottom flask. The volume is going to start to increase. There's going to be quite a bit of fizzing. And we will see the temperature increase in the round bottom flask. Because we're getting right up there, 40 degrees, I'm going to try to cool this round bottom flask down a little bit. I've got some ice handy. I'm just gonna take a piece of ice and throw it into the water bath to help decrease the temperature. And I'm also gonna slow down the hydrogen peroxide and give this a bit of a chance to react. We definitely don't want to have any of this solution fizzing up into the joint where the Claisen head is attached to the round bottom flask. We also don't want it to get too hot because we don't want any side reactions taking place. So we're just going to allow the hydrogen peroxide to finish adding to the round bottom flask, monitor the temperature to make sure that it stays below 40 degrees, and also monitor the reagents to make sure that they don't foam up too high in the round bottom flask. Once this is done, we're going to allow the solution to sit and stir in this warm water bath for at least a half of an hour. The reaction is now complete and it's time for us to separate our product from the mixture of chemicals inside the round bottom flask. Let's begin by thinking about what we have present currently in the round bottom flask. Right now we have two solvents in the flask. We have THF, tetrahydrofuran, and we also have water present. THF and water are soluble in each other. The THF molecule is a really small cyclic ether. It's capable of hydrogen bonding with the water molecule, so these two solvents dissolve or mix together, and currently we just have one layer inside this round bottom flask. Inside that layer, we have our product, the hexanol molecule, and then we have any kind of leftover unreacted reagents and stuff mixed in there as well. One of the challenges that we have with separating and isolating this hexanol product is that it is slightly soluble in water. It's a relatively small alcohol, so it is somewhat soluble in water. In order to help get this alcohol out of our water THF mixture, we are going to use a technique called salting out. In the salting out process, we are going to add an ionic compound. Ionic compounds also are referred to as salts, so that's how this gets its name. We are going to add an ionic compound to this mixture. The ionic compound will dissolve in the water because it is soluble in water. And as the ionic compound dissolves, this causes the polarity of the aqueous solution to increase. Having all those ions running around inside the water layer will increase the polarity of the aqueous solution. As the polarity of our aqueous solution increases, the solubility of our hexanol is going to start to decrease. So this causes a decrease in the solubility of our alcohol in water. And so that's going to help us remove the alcohol from water. So we're going to begin by adding an ionic compound to really increase the polarity of this whole entire layer. And then once we've finished that, we're going to come after this with a very organic solvent, a very nonpolar solvent that will not dissolve in the THF water mixture. And the hope is that this alcohol will move out of the water into this new introduced organic solvent. Let's watch and see how it works. So here's our mixture. We are ready for the salting out process. We're going to be using anhydrous potassium carbonate, 20 grams, which is a ton. I am going to be adding it to the round bottom flask using a powder funnel. A powder funnel has a really wide opening on the bottom, which makes it ideal for adding a powdery solid such as the potassium carbonate. There is so much potassium carbonate going into this flask. What we're trying to do is create a completely saturated aqueous layer. Not all of this potassium carbonate is going to be dissolving, and that's fine because that's how I will know that I have completely saturated the aqueous layer. Once I get it all in there, I'm going to put a stopper on it and I'm just going to shake it for a minute just to make sure that it gets completely saturated in the aqueous layer. I'm going to pour this solution into the separatory funnel. Look at all the undissolved potassium carbonate in this flask. It is really important that I don't transfer any of the undissolved potassium carbonate into the separatory funnel. It will clog up the opening of the stopcock on the separatory funnel. So I'm going to pour super carefully. I'm not going to be able to get everything out all in one pour, but I'm going to get as much as I can without getting any of the solid transferred. And then I'm going to be using some hexane. I've got a little bit of it measured out already. I'm going to pour that into the round bottom flask, swirl it around a little bit, and it's going to give me an opportunity to pour some more into the separatory funnel. Again, without having to worry about accidentally getting any of the potassium carbonate into the separatory funnel. Because I've kind of agitated the potassium carbonate a little bit, I'm just going to set it aside for a second, kind of let it settle down. And then I'm going to come in with some more hexane, and I'm going to do another transfer. I am again just trying to get everything rinsed out of the round bottom flask, transferred into this separatory funnel without transferring any of the undissolved potassium carbonate because it will clog the separatory funnel. So this looks like I have got a really good transfer, and I have two clear layers inside the separatory funnel right now, a white layer and a brown layer, and I'm just going to begin the extraction process. So I'm shaking, I'm venting, and right now, hopefully what's happening is the hexanol is moving out of the aqueous polar layer and into the hexane layer, which I've just added. We can see a really nice separation of the two layers, kind of that yellowish layer down on the bottom, that's our aqueous layer, and then the brown layer up on top, that's our organic layer. The product should be in the organic layer. Next, I'm going to be draining the aqueous layer out of the separatory funnel. The aqueous layer is the bottom layer that is currently kind of a light yellow color, and it does not contain our product. Our product is in the top layer, which is that dark brown color. Our product is not dark brown. That dark brown color is due to the presence of unreacted iodine, and we don't want any of that present in our product as well. So once I get the aqueous layer drained out, I'm going to be adding some 30% sodium thiosulfate. The sodium thiosulfate will react with the iodine. It will convert it to iodide. You will be able to see this actually happening because the color of the solution is going to change from this brown color to colorless as all of the iodine reacts. It's not going to happen instantaneously, it's going to happen while I am shaking. So let's just kind of go ahead and watch the color magically disappear. Now that both our layers are colorless, it makes it a lot harder for us to see the interface between the two layers. But I'm going to pull the SEP funnel out and kind of swirl it around. Hopefully you can see the interface kind of swirling around towards the bottom of the separatory funnel. The aqueous layer is still down on the bottom of the separatory funnel. Remember, our product is in the organic layer, which is on the top of the separatory funnel. Once this has a chance to sit and settle for a bit longer, I'm going to drain the aqueous layer out of the bottom of the separatory funnel. It is waste, and we're going to continue to work on cleaning up the organic layer. I'm draining the aqueous layer, and once it's completely removed, I'm going to add some saturated sodium chloride. The saturated sodium chloride is going to rinse any ionic byproducts or unreacted reagents out of the organic layer. This is going to help purify and clean the organic layer. So hopefully when this process is done, all that we have left is just our hexanol molecule. Once the layers have a chance to settle and separate, I'm going to drain the aqueous layer again, and then I'm going to repeat this same process with the saturated sodium chloride. 2 rinses with saturated sodium chloride should be enough to get all of the impurities rinsed out of the organic layer. The separation process is complete, and now I'm going to transfer the organic layer into a clean beaker. The organic layer contains the hexane solvent as well as our product, 1-hexanol. Because the separation process involved the use of several different aqueous solutions, such as the saturated sodium chloride solution and the 30% sodium thiosulfate solution, it's reasonable for us to assume that some water might be trapped in this organic layer. And so our next task and our last task is to clean up any water that might be stuck in this solution. To do that, we're going to be using a drying agent called sodium sulfate anhydrous. The sodium sulfate serves to absorb any water that might be present in this solution. To use a drying agent, you'll just put a small scoop of the powder into your solution. The exact amount doesn't really matter, but you don't want to add too much because you don't want to be wasteful. Once you get that small scoop in there, you'll swirl it around inside the solution and just take a look at what happens. This drying agent is not going to dissolve, it's going to stay solid inside that solution. What you're looking for is the behavior of the drying agent in the solution. If the drying agent clusters or clumps together, that means that it is actively absorbing water. And if it clusters or clumps together without any free grains present at all in the solution, then you just need to add a little bit more. Swirl and observe the drying agent in solution. Again, it's never going to dissolve. All that you're looking for is the way that it behaves inside the solution. Does it clump together or do the granules stay separated? This particular solution takes a lot of drying agent. Normally it just takes 1 or 2, maybe 3 small scoops before the solution is dry. But in this situation, we're going to end up adding a lot of drying agent, like an abnormal amount of drying agent. As the drying agent works, it's absorbing water out of the solution. The granules that have absorbed water are always going to stay clustered or clumped together. So we're not going to expect them to separate from each other. We'll expect them to always stay clumpy. What we're looking for are the addition of a scoop of granules that doesn't clump together. So again, everything that was already clumped is going to stay clumped, and we're just hoping that maybe this next scoop that we add won't clump together and those granules will stay free-floating. Once we get to that point where we've added enough drying agent, we will carefully transfer the liquid only into another clean beaker. We're going to be leaving behind the drying agent because it's served its purpose and we don't want it in our final product. So once I've decided that I've added enough drying agent and all the water has been removed, I'm going to very carefully pour this solution into another clean beaker. I'm going to leave behind all of the drying agent. And once that's done, I'm going to set the beaker aside overnight and let the hexane evaporate. The hexane will evaporate and it will leave behind just the one hexanol product. And the next day we will analyze the product just to verify that it actually is one hexanol. That we're going to verify that we made one hexanol instead of two hexanol is by measuring the boiling point of the liquid. There is a couple ways that you can measure the boiling point of a substance. The easiest way is to use the same apparatus that we use to determine the melting point of a substance. So we're going to be using one of these little tiny capillary tubes, and we just want to put a very small amount of our liquid in the bottom of this capillary tube, just like we would do with a solid, and then stick it in the machine and watch it boil. So one of the challenges with this is that the opening is so tiny with these little capillary tubes that it's really difficult to get the liquid down into the capillary tube. So in order for us to be able to put our liquid in this capillary tube, we are going to make a really skinny pipette from this glass pipette. So what I'm going to be doing is heating this pipette up, this glass pipette up in Bunsen burner flame. I'm going to be heating it in the hot part of the blue flame, and I'm going to be heating around the midpoint of the pipette. Once the glass starts to feel really flexible, I'm going to be able to pull it apart. So I'm just going to be pulling it this way, and that's going to create a really skinny tip on the pipette that I will be able to stick down into the capillary tube. I haven't done this in over a year. This is my first try. I didn't even practice, so it might be pretty bad. But we'll see. I don't know if you can see that the glass is starting to get really flexible. I'm rotating it, trying to keep a nice even heat on the pipette. And then when I think it's ready, I'm going to pull it out of the flame and pull it apart. I actually did a pretty awesome job for this being the first time that I've done this in a long time. So obviously we don't want a pipette that is this big. We're going to be able to snip it into a smaller pipette, but we definitely want to let this cool down before we start putting our hands on it and trimming it into something smaller. So I'm just going to set it down and let it cool down, and then once it's cool, we'll cut it into a smaller size. Okay, so we have let this cool for a bit, and what I'm going to do is snap this to make an actual pipette. This is the top of the pipette where we're going to fit the bulb. So down here somewhere is going to be the bottom of the pipette. What we want to do is just kind of err on the side of caution. So I'm going to snap it probably further down than I think that I need, because I can always snap more off later if I need to. And then what I'm going to do is just check to see if this is actually small enough to fit into this capillary tube, which it looks like it is. So since I'm able to fit it into the capillary tube, this is going to work for dispensing my alcohol, the hexanol. It's actually really, really long, so I'm going to try, this might be dangerous, but I'm going to try to cut a little bit more off the end. Hopefully it will still fit in the capillary tube. If it doesn't, that just means that I made a mistake. No, it still fits, so we're still good. And this is still pretty tricky process because this is so small. Fortunately, we don't need very much of the alcohol to get the boiling point. So I'm just gonna suck a little bit of it up into this pipette. And then I am going to transfer it into the capillary tube. As you can see, it's kind of like threading a needle. It's not a super easy process. Because my liquid has really sucked up into the top of the pipette, I'm going to take the bulb off and I'm going to try to use the bulb to blow the liquid down into the bottom of the capillary tube. And it has worked. There's a really small sample down in there, but remember, we don't need a large sample because it's going to be magnified in the melting point apparatus. So the last thing I'm going to tell you before we stick this into the machine is that this pipette that we created to help put the liquid into the capillary tube, we're actually going to leave it in the capillary tube. As the liquid boils, it's going to be boiling off of the opening of the pipette that we created. So we need to have the tip of the pipette in there as a reference point to help us be able to tell when the substance actually starts to boil. Our capillary tube is in the center spot of the melting point apparatus. And what I'm doing right now is just raising and lowering the pipette that we've placed in the capillary tube, just so you kind of have a reference of where it's located. It is literally all the way down to the bottom of the capillary tube. As this substance approaches the boiling point, it is going to start kind of moving around. It almost sort of looks like a lava lamp in there. This is indication that we're getting close to the boiling point. But what we're looking for, and that would denote the actual boiling point, is literally bubbles. We're going to literally be able to see very small bubbles coming from the bottom of the pipette and rising up the capillary tube. So they're going to look like they're appearing pretty much at the very bottom of the capillary tube. And it's moving quite a bit now, so we should be seeing bubbles at any minute. There, I just saw a bubble go by. There's another bubble. So there are our bubbles. They're very, very small bubbles, but you can see them coming like right up the center of the capillary tube. This is 153 degrees Celsius. So when we are putting a sample on the IR, we have to use the correct tip based on whether we're dealing with a solid or a liquid. The last time we were dealing with a solid, which is when we use the flat-bottomed tip. This time we have a liquid, which means we're going to be using this tip that's kind of concave in. I'm going to begin by attaching the tip to the arm. It just screws into place. And then I'm going to put a small amount of our alcohol onto the diamond of the IR. And then I'm just going to drop this tip down in place. It just kind of holds the alcohol in place while the IR spectrum is measured. Just in case it's volatile, that'll keep it from evaporating. So I've already run the background on this and we're ready to just go straight to the sample. Hopefully we're going to find that this is 1-hexanol. Remember, this particular set of software always gives us the spectrum upside down. So initially it's going to look kind of funny, and then we're going to have to move the spectrum in the correct direction. But even looking at this initially, this actually looks really bad. This absolutely does not look like the spectrum of 1-hexanol. Now it looks like we're going to have a little bit of an OH peak over here, but it just doesn't look right. Let's get this turned around. And what I've actually done is pulled up a reference spectrum for, oh, that's for butanol. I'm gonna have to edit this shit out.
You just edit on a picture of 1-hexanol.
actually doesn't look bad at all. Looks okay. Okay. So I'm gonna pick a few peaks here. It's not a great looking spectrum, but maybe we'll find that the peaks are in the right spot. And I'm gonna print this so that we have this for reference.